In this video, I'll go over every mate in SolidWorks assembly and give an example of each. Jumping straight into it, some useful tips and tricks in the SolidWorks assembly. First one is that you can press the tab button when you're hovering over a part, and that will make that part disappear. And if you want to bring that part back, you hold the shift key on your keyboard and press tab, and it brings it back. So this is useful if you have parts that you quickly want to hide and get out of the way. Second important point to note is that parts are floating except for the first part brought into an assembly. It's fixed by default. So to fix or float a part, you can just right click it and either hit fix and then it's locked in position, or hit right click and hit float and then you can move it around. Lastly, all mates can be found at the bottom of the assembly tree, so just over here on the left, and mates specific to a certain part can also be found in a mates list under that part name as well. So it's a quick way to find them. So I'm sure you all know that mates are a way of combining parts in an assembly, but if you go to mate and hit the icon, jumping into it, the first one is the coincident mate. So this is essentially to make parts touching each other. So we can do two planes that are coincident like that. And then once they're selected, they can move around but stay touching. Or you can also make edges coincident. So here I'm selecting two edges. And interestingly, I can actually just make points coincident as well. So if I select these points. And now this is more or less a hinge, but this isn't actually the way you would make a hinge. So coincident is just joining 2 points, planes, or lines together. Likewise, you can also select a parallel mate. So for this example, I'll make these 2 planes parallel, and then I can adjust the distance between them as needed. Also similarly is the perpendicular mate. I'll select 2 planes, and that just makes these 2 planes perpendicular to each other. Next one is the tangent mate. So I can select a circular edge and another one, and this will keep the 2 planes tangent to each other in this case. So I actually might want to select another coincident mate just to keep it locked on that plane. So I might use this in a case, say, where I want to position, a bearing or something around a cylindrical profile if I just want to quickly move it around. If I also had some kind of wheel that's rolling on a track or a flat surface, I can use the tangent mate to achieve what I want. Next up is the concentric mate. So this is a very commonly used mate in SolidWorks. Generally in mechanical engineering, rotary motion is a big thing you're dealing with quite often. So here I select the outside of this bearing and the inside of the protrusion, the bearing sitting inside. And I can also choose the option of lock rotation, which just depends on the situation. In this case, I'm going to select it because this would be a bearing that would be press fit into here, so we don't want that to rotate. Likewise, I also used a concentric mate to mate the inside of this bearing to its outer portion. And I didn't use the lock rotation in that case, so I can rotate this around freely. Next we have the lock mate, so I can simply select 2 parts and effectively lock them together in the position they're currently in. So once I do that, then if I move one and drag one, the other will follow around with it. Then we have the distance mate. In this case, I can select 2 planes and then select the distance. So by default, it will make those planes parallel to each other. And if I want to put in a specific distance between them, I can. I can also flip the dimension between them. And finally, for the last standard mate, I have the angle mate. So if I have 2 planes that are maybe fixed along an edge, and then I select the angle mate and both of them, I can put in a specific angle that I want. So say 45 degrees, I can flip that dimension or flip the alignment, and that will just get me a precise angle input. Next, moving on to the Advanced Mate tab. The first one is the Profile Center. So this is essentially used to align the centers of 2 square or rectangular profiles or 2 cylindrical profiles. So if I select one of the rectangular faces and another one, it will just align the sort of centroid of them and bring them coincident to each other. So you can do that just with coincident mates, but this sort of saves you a few clicks and does it all in one mate essentially. Next in the Advanced Mate tab is the Symmetric mate. So another quick tip, if I quickly want to copy a part, I can select it in the assembly tree and on my keyboard hold Control and click C for copy, and then hold Control and click V for paste, and it just pastes a copy in. Going back to the Symmetric mate, I find it most useful to use this with a plane in the part. So if I go to this part that I just copied and select, say, the front plane, and now I want to make that symmetric between two other faces in my assembly. So I'm going to select these two faces here, and that's just positioned the sort of plane from this part, the front plane, symmetrically between those two faces on the other part. Looking at this other assembly now, if I want to position this block inside this channel, then a useful mate for that is the width mate. So here it's similar to the Symmetric mate, but I'm actually selecting two parallel planes on one part and then centering them between two planes on another part. So just like that. So that's centered it in one direction. Then if I want to use the width mate again and select these two planes which are in the opposite direction. And now that's centered it, so this is running through the center of this channel. A benefit of using the width mate compared to just using maybe a coincident mate or a distance mate is that you can then modify the dimensions of one of these parts, make it a bit bigger or a bit smaller, and the width mate will update and it will stay centered according to your intent. Next, looking at the path mate, this can be used in a variety of different ways. So suppose I have some path which is represented by a sketch of a spline on a surface, and I've got a point that I want to follow that. I can select the point, hold Control and select the path and go into Mates and select Path Mates under Advanced tab. So then hit OK. So now this point will follow the path. I might want this to be aligned vertically, so I can select the top face of it and the face of the plate and make them parallel. And now I have this point which will follow this path. A slightly more interesting example is perhaps I have some kind of spiral and I have the path drawn out, and maybe I want this ball to follow this path. So pre-modeled that in, but if I go in a point which is represented by a sketch in the center of the ball is mated to a spiral. So can use the path mate in a series of ways to get a point to follow a path essentially. Next up is the linear coupler mate. So an example I have for this is a telescope mechanism. Let's say this is comprised of a series of smaller concentric cylinders. Let's say we want this telescope to kind of expand out evenly. So, you know, when we drag one of the elements to the end, the whole thing sort of expands out. So at the moment, each one is just mated concentrically, so I can drag them individually. But if I wanted them to all move in unison, how might I do that? Well, I can use the linear coupler mate. So let's say we want this face, as this face moves out, we want this face to also move out. Now, as we imagine that we're moving out from this reference face here, for every 1 millimeter this face moves out, we want this one to move out 2 millimeters. Well, we could actually leave it as 1, and I'll show you what happens in that case. They both just move out together. But for this telescope example, we actually want the second one to move out double the distance away from this reference face. So now in this case, they're both kind of expanding. So I'll just put in one more. So the original movement face and then this one. And now we want this one to move out 3 millimeters actually from the reference face. So now if I drag one of these, you can see they all expand out together. Obviously, I could set some limits so they don't overshoot, but that's an example of the linear coupler mate. Next, we have the limit distance mate. So say we have a linear actuator and the rod can sort of expand and contract. Maybe I want to set the limits accurately to represent the actual range of this physical product. So I can do that with a limit distance mate. I'll select the end face of the rod and the end face of the housing. Maybe I'll select my minimum distance to be 5 millimeters and the maximum to be 80, just as an example. Hit OK. And now I've set some limits on that. And if I were to bring this over into another assembly as a sub-assembly, as long as this sub-assembly is flexible, it will remember this limit distance mate. Similar to the limit distance mate, we also have a limit angle mate where you can select two planes and select the minimum and maximum angle you can move those planes between. So I use that extensively in modeling this human figure. Obviously, because I want it to be anatomically accurate and don't want the joints bending in the wrong directions. Another useful thing you can use is a mate controller. So if you have many limit mates, in this case many limit angle mates, you can't really easily and reliably move them around just with your mouse by clicking and dragging, because there's so many. So if you set up a mate controller, which you can do by just searching for mate controller in the top right help bar, I've set up limit angle controller mates for each joint here. So for the elbow, for example, I can bend it to a maximum of 120 degrees or a minimum of 0 degrees. Just one thing to note with the limit angle mates is occasionally they will flip directions. They seem to have a mind of their own sometimes. You can use a reference entity, which is a third axis. I'm not going to cover that in this video, but even still, sometimes they have a mind of their own, so just be aware of that. Okay, next moving on to the mechanical mates. So the first one we have is a cam mate. So suppose we have some kind of rotational cam, this avocado looking thing here, and I've got some pin that I want to follow this as it rotates around. So I've already mated this so it's constrained to an axis. Now I can go and select the cam mate and select the cam surface. And here I've got a point which is a sketch that I'm selecting. And then go like that. And now as I rotate this around, this follows this with this cam mechanism. Moving on to the slot mate. So if we have a slot in some kind of part and some pin that we want to follow that slot, so this is an expanding pulley mechanism I have here. So I'm going to go into mates, mechanical mate, slot, select the pin and then select the corresponding slot. I want this to be free. I could also specify a specific position I want it to be locked at. And now as I rotate this, as the slot moves, it pushes the pin around. So another useful thing I can do is do a circular pattern. So I'm going to select my bodies that I want a circular pattern and then select my direction. And I want 6. And that also patterns the slot mate. So now with this mechanism, as I rotate this out, the slot mate pushes all the pins up and down. And these are just sliding up and down in channels. So it's an interesting example of the slot mate. Next up is the hinge mate. So this one's pretty self-explanatory. Just select the concentric selections and then coincident selections and creates a hinge. So obviously you could produce that with separate mates. I guess they just decided to put it in one to save a few clicks because hinges are pretty commonly used. Okay, next up is the gear mate. So I've already pre-mated these. I've mated these gears on these shafts and they are free to rotate. If I wanted to mate these gears, I just select two cylindrical faces on the gear. So in this example, I've selected these portions of this outside face, but I could also select the inner cylindrical bores, and underneath I can set the ratio. So I know this small gear has 10 teeth and the large one has 20 teeth. And if I do that as I rotate one around, it keeps the teeth meshing together correctly. And you can essentially think of the gear mate as just a rotational ratio mate. So you can use it to mate other things together. So in this example, I have this shaft that's rotating in this bearing. And if you notice carefully, for one rotation of the shaft, the balls only rotate, a fraction of a rotation. So what I've actually done is, if I just select the ball, I produced a sketch, just a circular sketch on the balls. Just open them up quickly to show you. So I have this sketch here. I actually didn't need it because I have a cylindrical feature in there, but you can go either out. And then I did a gear mate between the face of the inside of the bearing, or I could have chosen the shaft because they're rotationally locked together, and then that circular sketch for the balls. And I've set a specific ratio I want. So that way, as I rotate the shaft, the balls also rotate, but at a different ratio. So that's using the gear mate as well. So it's not just for gears. So next up, we have the rack and pinion mate. So in this case, I have a rack, which is meshing and moving with these gears. I can also move the first gear in the chain and it will update and move the rack. To do this one, I select the rack and pinion mate. For the rack, I select a edge or an axis in the direction of motion. And then for the pinion gear, a cylindrical face around the rotation. And then I can input my pinion pitch diameter, which I know to be 40 for this one. Or I could also put in the rack travel per revolution. So if you put that in correctly, everything, the teeth will stay nice and meshed correctly. Looking at the screw mate now, for this one I can select a cylindrical face of a screw or a bolt, and then the corresponding hole it's mating into, and I can select the distance per revolution, just choose 2 millimeters here. And now as I rotate this screw, it will move into the corresponding hole. I don't think it's very common that you would need to use this in this example. Generally, you can just do a coincident mate. In this case, I have a countersunk hole and a countersunk bolt, so a coincident mate just locks it in place. Or I could just do a concentric mate if I wanted to be able to adjust the position. But the screw mate may be useful in cases where you're replicating the motion of some kind of helical part or spiral. And the final mate of the mechanical mates is the universal joint mate. So if I have a universal joint set up with some slight deviation in angle, I can go into mates and do universal joint and just select two of the corresponding cylindrical faces on each side of the joint. And now when I rotate one, the other will rotate. Just a note that this actually isn't necessary if you model the interior cross-link between the sides of the joint. And I've just made these concentric with each opening. So the universal joint mate is just to save a bit of time if you don't want to go through the effort of doing that. And that's all the mates in SolidWorks. So if you found this video useful or interesting, leave a thumbs up, drop a comment if you have any questions, and like and subscribe. Thanks for watching.